I'll be talking about each of the individual component codes we have for the sensors. The first component I'll be talking about is the line following sensor. Our function handler reads all 6 analog values of the line sensor and updates their global value so the robot can detect arena borders. In the IR sensor, our function handler reads the IR sensor and triggers an immediate modal stop when an object is detected. For the ultrasonic sensor, our function handler triggers both ultrasonic sensors, reads echo duration, converts the distance, and detects obstacles within range. For our time of flight sensor, our function handler reads precise short range distance and detects small objects such as snow cubes. For the IMU function, we have two handlers. We have the angle update handler and the calibration handler. The read IMU continuously calculates the robot's rotation, while the calibrate IMU reads it computes the gyro drift while stationary. Then the motor controller sensor, we have the low level motor handler and the high level motor handlers. These functions let the robot perform actions like forward movements, backward movements, turning, and stopping.
Hello, my name is Sukash from Team Mandy, and I will quickly be going over the unit tests we did for our robot. So first I'll go over the IMU. So basically, this code is doing something very simple. It initializes the I2C communication with the IMU sensor, and it basically just reads all of the accelerometer, gyroscope, and magnetometer as well, and just ensures that they're printing out correctly. We only really use the accelerometer for our robot, but we ensured everything else was functional just to make sure the component itself wasn't broken. Next up, you have the IR sensor. This is a very simple test. It's basically just reading high or low if this IR sensor is getting anything, and then it prints. If it's low, it passes. That's the obstacle. If not, then there's no obstacle, and we obviously do this test with an obstacle. Next up, you have the line sensor. Another simple test, just making sure that each of the left, middle, and right pins are reading black or white based on if it's a low or high, low being black, high being white. Next, we have the motor driver. We tested the motor driver to make sure it works properly, just so we could test other stuff as well. And basically, what we're doing here is we're calculating pulse period and the RPM. And we basically want a pulse period between 25 milliseconds to 200 milliseconds, and then we also just basically want the RPM to be calculated during this test as well. So whenever we spin the wheels, we're able to see how fast it's going. Next up, you have the time of flight. Now, with the time of flight, unit test is basically testing is basically using a short distance, as that will provide the most accuracy when we're doing our implementation. And it basically just gets a distance in nanometers and then prints a pass or fail depending on if it detects an obstacle or not. Next up, we have the ultrasonic. So another distance sensor basically, it sends a trigger pulse, converts the time to distance, and then it does 3 tests. One, it makes sure the echo detection is working properly. 2 is making sure we can detect the obstacle within 100 centimeters, and as well as have some stability errors for plus minus 10 centimeters. And if it can detect an obstacle, then it's pass fail. And if you can't detect an echo, then nothing is detected as well. For the last test, we also tested the wheel encoders as well, as we were planning to use them at the beginning. We're using an interrupt on pin 2 for each encoder pulse, and we're basically just measuring the time between each pulse. So on the serial, you get the pulse of the period, you get pass or fail for detecting the pulse, and you also get the RPM calculations, which is what we were using this for the most.
I'm here to introduce our main function of the robot. We started by including the necessary libraries. Then we configure the pin for the hardware components. We map in the direction and PWM pins for our motors. Also configure the pin for all of our sensors. Then we declare the key variables such as our motor speed, sensor threshold, and flags. To manage our robot's behavior, we configure the robot state enum, which allow us to switch clearly between the state like idle, moving around, avoiding border, and avoiding obstacle. Moving on to the next part, we implement the specific handler and simple function for our motion control. The core of this part is the set motor speed function, which accepts the direction pin, a PWM pin, and the speed value. Inside the function, we handle the motor's direction by set the direction pin to high or low, and then we pass the PWM speed value. We create the move function such like move forward, turn left, and turn right, etc., which call the set motor speed function along with our defined speed value to let the robots moving under a speed constraint. For the next section, which are the sensors function. To ensure the detection reliability, we deploy 2 unit sensors for each different sensor type. We use the function called read line sensors to constantly read the data from 2 units of the line following sensor. Then inside the check border, we use OR logic to compare those values against our threshold. Basically, if either sensor in a pair trigger, we set a flag to tell the state machine which direction the boundary is in. We took a similar approach for our check obstacle function. To improve the performance of obstacle avoidance, we combine 3 types of sensor: ultrasonic, IR, and time of flight. They all follow the similar logic. If any one of them detects an object within a range, it returns true to immediately trigger the obstacle avoidance states. Then is our state machine implementation. In the moving around state, we originally used a continuous moving forward function. However, because our motors could not move at a PWM speed lower than 128, we had to implement a step move pattern instead. We just repeat moving, checking border, and stop. We then add a delay for each action to ensure the robot is not going out of the border. During the demo, our moving duration was set too short, so the robots moved very slowly. We later increased this duration from 50 to 280. The overall performance was much better. In the avoiding border state, we used the flag set earlier to decide whether to turn left or turn right, and then clear the flag once the turn is complete. For the avoiding obstacle state, because not all of our sensors working properly, we have to use the random turn strategy to avoid the detected objects. Finally is our standard Arduino setup and loop function. In setup, we initialize most of the needed pin and pin mode, and we configure the random state and configure the hardware watchdog timer, which reset the system from freezing. In the loop function, we execute the specific function here, and we run the state machine logic. That's all for the main function, and that's the end of our code review. Thank you for watching.